Good morning, everyone. Myself, Dr. T. Vasudeva Reddy. I am Associate Professor in the Department of ECE, B. Viraju Institute of Technology. Today, I am here to present my course on VLSI design and its applications. Some of the things that I am going to discuss today is prerequisites, course objectives, course outcomes, some of the textbooks that are required for the subject, as well as reference textbooks, and the companies that are hiring for the jobs, as well as what are the different roles we have in the job roles, as well as who are the hiring partners. And coming to the subject, introduction to integrated circuits and design of VLSI design flow. Coming to prerequisites, there are basically two textbooks that are required for this subject is Electronic Devices and Circuits by Jacob Millman and Digital Logic Design and Computer Design by Maurice Meno. Coming to course objective, interpret the different steps involved in the fabrication process of integrated circuits. Analyze the behavior of inverters using various design loads and develop a layout model for various logic designs and implement the logic circuits using CMOS technology, and also the implement relevant concepts for their academic projects. Some of the course outcomes: after completion of the subject, students will be understanding about the steps that are involved in the fabrication of integrated circuits and analyzing the behavior of inverter circuit with various loads. Apart from this, developing different types of layout designs for digital logic circuits and also implementing different logic designs using CMOS technology. Implement relevant concepts for their academic projects and for their future applications. Coming to textbooks, Shanghai, Douglas Bucknell are the basic textbook, and another textbook is Neil Waste for CMOS VLSI design, and FinFET devices for VLSI circuits and systems by Samar K. Saha. These are the basic textbooks that we are following as per academic norms. And some of the reference textbooks are John Uemura, SMZ VLSI Technology, and Introduction to VLSI Design by Mead and Conway. And as I said, there are different partners who are going to recruit the VLSI people is Intel, Synopsys, Cadence, NVIDIA, Analog Devices, Xilinx, Texas Instruments, Micron Technologies, Microchip, Bosch, Cypress, Microsemi, and Sankalp Semiconductors, Wipro, Digital Core, Arisen Technologies, Avantel, Path Partner, and Silica, Tata Flexi Electronics, Arise, Baker Hughes, Skywork, Avago, Tech Mahindra, and also finally the Qualcomm. So these are the industries they are working in the VLSI domain, and they are going to recruit basically the VLSI design engineers who are coming from the graduation. And what are the job roles that we have in the market? The job roles are front-end design engineers, verification engineers, physical design engineer, mask layout design engineers, and DFT engineers, post-silicon validation engineer, analog as well as mixed design signal engineer. Finally, FPGA designs. These are the job roles we have in the market. According to your interest, you can choose any one of these things, or you can prepare accordingly and you can go for the respective job roles. And as we know that there are many components and many products in our daily life which we are using is consisting of integrated circuits. Some of the circuits are given below, some of the products are given below. The one is smart product, smartwatches. The second one is video surveillance system and internet, which are connected many people at a time, and also our fish, sound systems, also smart homes. These are the different products that we are using in our daily life: mobile, audio system, routers, antenna, micros, and smart TVs. Apart from this, some of the industries they are concentrating on different products which they are using in electrical vehicle. If you see those kind of smart products that are GPS model, sensors, cameras, fuel sensors, ultrasonic, exhaust gas sensors, inertial sensors, tire pressure sensors, infrared sensor, radar sensors, micros, phone, video cameras. These are all integrated together to make a certain product. In order to function these different types of sensors as well as different models of a electronic designs, we need to have an integrated circuit so that we can able to work perfectly with the system. And when it comes to the another products, which a wireless communication system which consisting of a blind network, thin client, firewall model, again at the end thin client, which is connected with the server systems and consisting of number of controllers connected with the routers, and this can able to have number of networks and connected with wireless sensor devices. And behind all these components we have an integrated circuits which makes our work simplify as well as produce the outcome effectively. Okay, coming to course, we are going to study about a VLSI design, and the basic components that are required for VLSI design is NMOS transistors, PMOS transistors. A combination of NMOS and PMOS transistors together we can make it as CMOS, complementary metal oxide semiconductor devices. And coming to NMOS operation, NMOS turns on when the voltage is high and it off whenever the voltage is low. It means to say because of the number of electrons which are high, or the majority carriers in the N-type transistor is electrons which are high in the NMOS transistor, it is going to on for a higher voltage, whereas it is reversed for PMOS. And PMOS consisting of majority carriers holes, therefore it operates for the majority carriers of holes. So there is a inversion process in between this. Apart from this, a combination of these two things will gives us a CMOS logic where it consisting of both PMOS as well as NMOS. Okay, when it comes to structure, so it consisting of a PMOS and NMOS which is connected to VDD and ground, and input is given here and the output will be taken from this point. So PMOS is always called as pull-up transistor and NMOS is always called as NMOS transistor. Okay, we'll discuss more detailed about different types of logic design in further classes. So these are the basic components as I told you. So NMOS structure as well as PMOS structure, a combination of N and P will give us CMOS structure. With the help of this CMOS, the basic component that is involved here is inverter circuit consisting of A is the input, then we'll have A complement is the output. So it means to say that whenever we apply A is 0, then the output becomes 1, and when we have input to the A is 1, then it will becomes 0. So basically it is an inverter circuit which complements the input signal. So this is the symbol for inverter circuit. So this is the basic element that is required to design different types of logic circuits. Coming to an integrated circuit, what basically is an integrated circuit? Integrated circuit is a complex set of electronic components that are interconnected together and imprinted on the silicon slice. So it means to say that we consider number of electronic components together to make a certain product, and that will be framed on the silicon wafer or slice. So here you can see different types of models of integrated circuits. One is a dip package and flat package and quad package. So based on our requirement, we are going to consider different types of package models. And coming to MOS technology, a MOS technology is split into different categories. The one is bipolar technology, second one is CMOS technology, the third one is BiCMOS, which is a combination of bipolar as well as CMOS. And the next one is silicon on insulator, and a combination of silicon and germanium is the other technology, that is germanium and gallium arsenide technology. So these are the different classifications of IC technologies. And earlier version of the IC technology is BJT, and later we have moved down to CMOS technology. So let us see what is the differences between BJT as well as CMOS. When it comes to power dissipation, it moderately high, whereas when it comes to CMOS, it is less, comparatively less. So it means to say that the amount of power consumption, when there is more, obviously there will be some amount of power dissipation. So the power consumption as well as power dissipation is proportional. So this power dissipation is high in case of BJT, whereas in CMOS it is less. Coming to speed, it has faster in speed, whereas CMOS technology is less in speed. Transconductance, when it comes to transconductance, 4 milliseconds is here in BJT and here is 0.4. And when it comes to switch implementation, it is a poor in its operation, whereas it has effective in its functionality. So switching implementation is the first thing that we consider whenever we are going for a functionality measurements. Then when it comes to technology, it is of lower in technology, whereas when it comes to fast CMOS, it is of faster in more. Okay, so considering all the advantages of CMOS, we have moved on to CMOS technology, and the basic advantages of CMOS technology is the power consumption is less as well as power dissipation is less, and it has a higher package density. What do you mean by package density? It means more number of components we can integrate together to make a certain functionality, and scale down more easily. So it means we can integrate n number of components as per our requirements. Accordingly, we can scale down the technology. Therefore, we can have n number of functionalities in integrated circuits. And fully restored logic level. So the restoring logic is fully applicable in case of CMOS design, and approximate rise and fall time in case of CMOS technology, whereas in case of BJT it is different. So considering all these advantages, we have moved on to CMOS designs, CMOS logic. Okay, introduction to IC technology. So the first version of integrated circuit is SSI, small scale integration, which consisting of the number of circuits 1 to 100 on a single silicon wafer. Example, gates, flip-flops and op-amps. When it comes to medium scale integration, MSI, so it has number of integrated circuits, number of components in a circuit is 100 to 1000. Some of the examples that here is counters, multiplexers, adders, 4-bit microprocessors. And the other technology is large scale integration, which consisting of 1000 to 10,000 number of components which are kept on a silicon wafer. And example is 8-bit microprocessor, ROM and RAM, random access memory. And coming to VLSI technology, very large scale integrated circuits, it has a number of components which starts from 10,000 to 1 million. When comparing with the existing designs, the previous versions, we have higher number of components here. And some of the examples that these number of components available here are 32-bit microprocessor, some of the peripheral components, and complementary metal oxide semiconductors which are of higher in MOS. And ULSI, ultra large scale integration, where it has more number of components that starts from 1 million to 10 millions. And gigascale integration circuit, which has the number of components are more than 10,000 million components on a integrated circuit. And examples, embedded system design and SOI model or SOC model. Okay, so now we'll move on to the what are the different types of integrated circuits that are available for doing certain functionalities. Hope the point is clear. So the integrated circuits are classified in two ways. The one is linear integrated circuits or analog integrated circuits. The other one is digital integrated circuits. Okay, so the basic difference between the analog integrated circuits and a digital integrated circuits is it takes the inputs as analog, operates the analog signal, and it produces the output in the form of digital. And when it comes to digital integrated circuits, it takes the digital signal as input and it produces the output. Some of the examples that are shown here are op amps, power amplifiers, multiplexers, comparators, regulators. So all these are analog components that can operate with the analog voltage, analog input. And when it comes to digital integrated circuits, some of the circuits that we have here is logic gates, flip-flops, counters, calculator chips, memory devices and microprocessors. So all these comes under digital integrated circuits. Now let us see the VLSI design flow, how right from input to the output, how we are going to consider the model. So coming to VLSI design flow, the basic step that we need to consider here is system specifications. So system specifications are we collect information from the customer what exactly his requirement is. So he will be giving his requirements. As a design engineer, we need to add some of the other functionalities like power, area, speed. As a design engineer, we need to add these things along with his functionality. So it means to say that the functionality is the primary one that we need to consider. Along with that, some of the secondary aspects are power, area and speed. After considering system specifications, we are designing a model in terms of architectural design. So it means we are writing a high level language coding using Verilog or VHDL model or system Verilog. Then we are moving on to the functional design. So here we consider some of the design models like RTL, register transfer logic, and the functionality we are defining here, and based on the functionality the circuits will be connected one to one. Then we will be moving on to its synthesis. Then after synthesis it is moving down to the next step, that is circuit design. So here in this case registers are converted into circuit level modeling. Then we consider number of components which are connected together with help of nets. Then we are going to prove its functionality once again. If the functionality is not proper here, then we move on to the architectural design. Then if the functionality in this case logic synthesis is not correct, then once again we are going back. Then in all the way, if the function is correct, functionality is correct and the logically it is proven, then we are moving down to circuit design. Then we are going to the next case, that is physical design. So this part comes under back-end design, where the first three blocks comes under front-end design. It means to say that in the functionality is proven in the front-end design, where the secondary aspects of power, area and speed are considered in the back-end design. So it means to say that in order to prove the functionality, we need to consider first the specifications RTL design, then logic design, then circuit design. So considering these things, we can say that functionality can be proven. So later on, we move on to the physical design, where physical design consisting of number of nodes, nets, then number of gates which are converted into the physical format, and these are laid down on a silicon wafer, and we go for its verification of its functionality along with power, area and speed. So it means to say that these power, area and speed are considered as a secondary aspects, and also we do that, we go for DRC verification. So DRC is nothing but design rule check as well as lambda based design verification. In all the way, I mean to say that considering design rule checker as well as lambda based design rules, then we can say that we can move down to the next case, physical verification. Once it is done, then we move on to the fabrication. Then in the fabrication process, we generate, we consider here once again the netlist and its amount of time intervals, and then we move on to the fabrication. So before going to the fabrication, once again we go with area measurements, delay, power or speed. So it means to say that considering the secondary aspects which are perfect in all the way, then only we move on to the packaging. And once after considering the package, we go with the aluminum packaging type. Then there are different types of packaging versions again, and we go for a testing whether we have done effectively, we are able to effectively manage the thermal constraints or not. So thermal parameters we are going to analyze after considering the package. Then we go for testing part. Then after testing, once again we go with chip designing on a silicon wafer. So in all the way, it means, I mean to say that in order to prove certain functionality of a integrated circuit, we need to consider the front end design in terms of functionality, back end design in terms of power, area and delay. Once after proving all these things, then we move on to the generation of bit file that is given to the fabricator. Let us speak more in detail about the physical design. In physical design, we are going with the partition of the integrated, partition of the design based on the functionality, based on the supply that it occupies and based on the flow that it has. And then again, we divide the chip into number of partitions. Then partition is done based on these things. Next, we go for a floor planning, and whatever the chip, whatever the component that are taking equal amount of power, we keep at one place, so that we need not to apply again and again the different voltages or the same voltage for different places. So in all the way, we can say that a components which are taking equal amount of logic, or a components which are having equal amount of logic, that can take only a single voltage. Say for example 6 volts. A 6 volts is the components which are taking all the 6 volts may be kept at one umbrella. A components which are taking 9 volts kept at one umbrella. A components which are taking 12 volts may be kept at one umbrella. So considering all these things together, then we move on to the placement, fixing a component at a particular place in order to avoid the much area. Then we go with the clock synthesis. So clock tree synthesis is a single clock that is applied to the entire system by dividing the clock into number of sublocks. Okay. Then we go for a routing path, making an interconnection between one component to the another component based on its flow from the input to the output. Then we go to measure a timing enclosures. How much amount of time is taking between each module, then what is the total that is consumed by the circuit. So it means to say that based on evaluation of time intervals, then we can have how much amount of delay it has. So in order to measure the delay exactly, we need to go for timing enclosures. And coming to the integrated circuit advantages, the basic thing is very small in size. As we know, the technology is upgrading day by day, and we have moved on from 360 nanometers to the 7 nanometers right now. So there are number of components that can be incorporated in a design. Therefore, we can have multiple functionalities. This is the advantage of small in size. As millions of components can be fabricated at a time, the cost for a particular integrated circuit can be minimized. And using different types of power consumption, power reduction techniques, we can have the amount of power can be minimized. The amount of power consumption can be minimized. It's highly reliable, and the operating speed is very high, as well as external wiring connections can be avoided so that the delay can be minimized. And we can, it has ease of use. So for based on the requirement of the customer, we can have n number of functionalities in a design. Therefore, for an integrated circuit can be applicable for n number of models based on the type of model and type of design. Thank you.
Vishnu Audio Visual Center, like and share and subscribe and click bell icon.